Okay, we'll continue our discussion with the graphs of tangent and cotangent. So, previously, these were the two graphs that we discovered for tangent and cotangent. So what we'll do is look at some of the similarities and what makes them unique. First thing, if I highlight just this one segment, this we'll consider to be a primary cycle. So if we're focusing just on this one, just like when we did sine and cosine, we noticed that the graph continues forever in both directions, but we focused on just the portion from 0 pi to 2 pi when we did sine and cosine. So here we're focusing on a main or major or primary cycle for tangent. For cotangent, this would be the primary cycle. First thing we're going to look at is what distinguishes one from the other. Notice that tangent tends to have the right side up, while cotangent doesn't. So there's a mnemonic device we could use to help us or at least remember or recall that tangent has a graph that the right side is up. The mnemonic device is, if you were to skip school because the weather is so nice and you went out and got a tan, when you return to school, somebody will know and you'll be disciplined and you will get a write-up. So tan, the tan that you got from skipping school, connects with the tangent function. The write-up that you receive because you missed school is the write-up, the side that tangent, the right side of it up, is on the upside. Second thing we need to be aware of is the boundaries that occurred, specifically the asymptotes. The left bound for tangent is located at negative pi over 2, while the right bound is at positive pi over 2. Whereas cotangent, the left bound is at 0 pi and the right bound is at pi. So these are critical points that identify or distinguish one graph from the other. Tangent, its shape, the shapes between tangent and cotangent, as you can see, are similar. But what distinguishes tangent from cotangent is the shape that it is going right side up. The second thing is its location on the Cartesian plane. Again, tangent has a left bound of negative pi over 2 and a right bound positive pi over 2, while cotangent, the O in cotangent, can help you recall that the 0 and the co kind of match up. So what we'll do is look at some of the terminology associated with these different functions. In y equals tan theta, we recognize that if I go back, let's do this. We can see that the graph continues this cycle or this repetition. So therefore, it is classified as a periodic function. Recalling, a periodic function is a function that repeats its value at regular intervals. And as you can see, tangent does fit that criterion. Next thing is that the graph does have these borderlines or these vertical asymptotes. The vertical asymptotes do occur at a particular interval. That interval is known as our period. The distance between any two vertical asymptotes for the graph of tan theta is exactly pi. So the period for tangent is pi. As compared to sine and cosine, the period was 2 pi. Next, we can see that there is this middle line per se. So it does have a midline. And the midline for tangent right now is y equals 0. Now let's talk about some of the things it's not. It's not sinusoidal. If you recall, sinusoidal meant it was a smooth, repetitive oscillation, like the graphs of sine and cosine. Nice, continuous up and downness of the graph. Additionally, there are no amplitudes. There's no distance to tell you how far to go to get to the maximum or minimum. So that flows directly into the next thing. There is no maximum and there is no minimum. Let's consider the domain and the range. Range is a little easier because range asks you how far down, how far up. As you can see, there's arrows going down, arrows going up. So the range goes from negative infinity to positive infinity. Or, one could have said, all real numbers. While the domain, because of the asymptotes, it gets a little bit more complex. Basically, the domain is all real numbers, because it could be anything, except where there's an asymptote. Well, all of the asymptotes are located at multiples of halves, looks like. Negative 3 pi over 2, negative pi over 2, pi over 2, 3 pi over 2. So what this is saying, we can take pi over 2 multiplied by some number n. The n has to be an odd integer. So odd integer like 1. Pi over 2 times 1, pi over 2. Next odd integer, 3. 3 pi over 2, 5 pi over 2. And I can do the same thing going backwards. So just to be aware that the domain has a special way of articulating. You're basically saying the domain is everything except where there's an asymptote. So let's look at cotangent. When we look at cotangent, it does the same thing as tangent with respect to it having this cycle or this it being a periodic function because it repeats itself. It does also have the vertical asymptotes. The distance between the vertical asymptotes are still the same period. So both tangent and cotangent have the exact same period of pi. The distance between these two asymptotes is exactly a distance of pi. Next thing, the midline is the exact same, y equals 0. The range is just like tangent. Goes on forever, going down and up, so all real numbers. While the domain is just like the tangent, all numbers from left to right except where there's an asymptote. And the asymptote here seems to be occurring at every multiple of pi. Negative 2 pi, negative 1 pi, 0 pi, 1 pi. And so here I'm taking pi and multiplying it by some number n. And that number n has to be an integer. Negative 2 is an integer. Negative 1, integer. 0, integer. So there's our distinguishing characteristics with tangent and cotangent. Let's consider the transformations. The general form of tangent and cotangent, just like sine and cosine, has these variables a, b, c, and d. The a does determine if the graph will reflect, recalling that a is not the amplitude. Tangent and cotangent does not have an amplitude. However, it still has a coefficient a. It will be used shortly, you'll see, but specifically, if it's negative, it will reflect. Next thing is the b. Just like before, it does assist with the period. Sine and cosine, period was 2 pi divided by b. Here it's just going to be pi divided by b. And this should be sensible or reasonable because in sine and cosine, the original period was 2 pi. And so to find the altered period, we take 2 pi divided by b. Whereas with tangent and cotangent, the original period is pi. So it should be reasonable for the formula to be pi divided by b. Next, the d, just like before, is the equation of the midline. Y equals whatever that number is. And lastly, was the part that was inside the parentheses, the bx minus c. This will be used to find the phase shift. Just like before, the formula is still the same, negative c over b. All right, and with respect to graphing, with sine and cosine, you needed 5 points. Well, with tangent and cotangent, it's not necessarily 5 points, but 5 distinct locations are needed to determine. The two things are, but the 5 distinct locations would be 2 asymptotes and 3 equidistant points. If you'll notice, on tangent, and there's cotangent, we have our 2 borderlines, which would be our 2 asymptotes, and then the 3 distinct points, or three equidistant points. So that's what one needs to determine in order to graph tangent and cotangent. So here's how we're going to do it. This is the graph that we will be using to help graph tangent and cotangent. Just like when we did sine and cosine, there were 5 vertical dotted lines and 3 horizontal. So our 5 vertical lines. The vertical lines 1 and 5, those will be where we locate our 2 vertical asymptotes, and the 3 equidistant points will be located on lines 2, 3, and 4. The midline will be located right in the middle horizontally, and then we would have typically gone up to find the maximum, but we're using this line. We're going to do the exact same thing we did with sine and cosine. Take whatever the value was for the midline and add the absolute value of whatever the coefficient was. So if we started at, say, 5, we would either go up, say, a distance of 3, and go down a distance of 3. So to locate the value on this bottom horizontal line, we take whatever the midline was and subtract the absolute value of A. So in the next lesson, we'll look at actually applying this. So we'll look at finding the 2 vertical asymptotes and the 3 equidistant points.